Okay, hello everyone. My name is Riley Dunn with I am 1/3 of JLR Solutions.
I'm Jessica Lee. I'm also 1/3 of JLR Solutions.
Hi, I'm Lindsay Pressler, and we are all in the Biological and Agricultural Engineering Department.
Yes, so our project takes place in Cuenca, Ecuador. We're working with the University of Cuenca, specifically Andres Alvarado. Our client there is Itapa, which is their kind of utilities government there. And then our faculty advisor is Dr. Gentrania. Our project manager is Dr. Nikolov. And like Lindsay said, we're in the Department of Biological and Agricultural Engineering. This next slide is a picture of the current site in Ecuador. This site services approximately 500 people and 100 hectares. As you can see from the picture, there's an inlet channel that goes to a septic tank, and then from there it goes to a constructed wetland. The second wetland is currently not functioning at the site, and there's been some talk about what to use that for, and then the potential space on the other side of the outlet is where we're looking at implementing a filter.
So the project scope was to focus on the disinfection of the final effluent being discharged into the Tarqui River. The main concern was for it to reach Ecuadorian standards for discharge in freshwater bodies. We also had a plan to not use any chemical use and low minimal pumping energy. The design constraints, which I touched on, are that the system is to reduce pathogens. Currently, the anaerobic system doesn't reduce pathogens to a safe amount. So a need for water to be reliable for public health and safety is to design for a goal of 4 log reduction. This also reduces fecal coliforms, and the natural filters with no chemicals will allow for possible reuse of the materials, and we wanted it to be low cost.
So our final design solution is a vermifilter and using recirculation to help continue to purify the water. So vermifilters are worm filters that have different layers of material. The top layer is dirt and earthworms, which do most of the purification, followed by a layer of sand and then a layer of gravel. These are separated by small screens just to keep the material from intermixing. So the worms require a wet and dry period for the water, typically about 1 hour of applied effluent and then 3 hours dry. This is to avoid drowning the worms and to make sure the worms can actually efficiently remove the pathogens and impurity from the water. So the earthworms actually consume pathogens and kill them that way. And they also secrete a mucus, which kind of traps bacteria in the coliforms and helps to kill them as well. On the next slide, we talk about more of our design constraints and what we actually picked. So we chose to build these filters in large water holding tanks like the one shown on the screen. This allowed them to be easily moved, easily sawed off the top of so they could be exposed to the air. We chose a hydraulic loading rate of 2.5 meters cubed per meter squared per day. This was chosen based on other literature and other research into vermifilters, which showed that this rate reduced the BOD of the water at the most. And while BOD isn't an exact measure of the fecal coliforms present, it does help indicate how much bacteria is in the water. We needed a daily flow rate of 86.4 meters cubed per day, which was based on the needs of the community. Based on these two numbers, we were able to calculate the area of material we needed, the area of filters we needed, and we came up with the combination of 3 tanks with a diameter of 3.8 meters each. These filters will be 1 meter high with 0.2 meters of worms, 0.4 meters of sand, 0.4 meters of gravel, and again, the wire mesh to separate the layers. Some of the advantages of this system is that worms are readily available in Ecuador. These systems have also been used successfully with dairy farm effluent, and there are some dairy farms in the Churubusco area. The vermifilter material on top can also actually be used as a fertilizer, and it's been shown to be better than chemical fertilizers. Some of the disadvantages are, though, is that the system isn't extensively tested. The worms cannot be submerged, so if too much effluent is applied and they don't get a dry period, or if there's a heavy rain, or if there's any kind of flooding, they will all die. And lastly, the vermifilters must be cleaned out every 7 to 8 months. The top layer has to go because there's just too many worms, too many have died, things like that.
So the second part of our design, we designed for recirculation of the effluent, and this would be an addition of a pump at the outlet of the filters to recycle it back through the system and essentially dilute the nutrients of the wetland to allow for more effective treatment. This will reduce pathogens and also dilute the bacteria, so increasing the holding time would only improve the quality of the effluent. Our proposed site diagram utilizes the potential space at the back of the site and will include 3 circular tanks with the recirculation pump installed.
The economic analysis for this project, the breakdown is in this chart right here, including the vermifilter cost as well as the recirculation cost. The most expensive part of this filter is definitely those layers, especially the worms. But it is a relatively low maintenance cost. The worms have to be replaced every 7 to 8 months, and that is the most expensive reoccurring cost. But then other than that, it's really just maintenance of the pumps and the piping and things of that nature. The materials of the sand and gravel need to be replaced every 5 to 8 years. So that's also pretty minimal. Overall, we're expected to be under $5,000 US for the total cost of the project. This is also all based on price of materials in the Cuenca, Ecuador area. To sum up our project, the vermifilters and recirculation meet all of the project objectives, including the low cost pathogen removal and an all natural system, as well as including some additional benefits such as being able to reuse the vermifilter material. We hope that this solution is something that will be able to improve the Churubusco site as well as other small rural wastewater treatment sites in the Ecuador area and can benefit the community there. On the next slide is our references that we used very frequently in this project. And we thank you so much for listening in and taking the time. Thanks, bye.